Number 10, anytime you see these like estimated to be an average of 23%, and then you see the keywords margin of error, all you have to do is do the plus or minus the margin of error to that estimation or whatever that average was. So if I start at 23% and I do plus 4%, we're going to get our 27. And then if I do minus my 4%, we're going to get our 19. So already I can jump to my answers that have those two percentages. To go through the other ones, it's not unlikely it's less than 23 because it can go all the way down to 19 because your margin of error is plus and minus that amount to give you like a more realistic estimate. At least 23%, that's not true either because again, it can go down to 19. Both of these have 19 to 27. Here's where we want to check our units. It's 23% of the students. So in D, you can see it's plausible that the percentage of the students is between 19 and 27. It's keeping our units consistent. In C, it's the sureness of the researcher, 19 to 27% sure. So they would have identified that in the passage. It's going to be students. It's going to be D here. Number 11, I see two lists of data, and they want us to compare the means to the standard deviations. So for means, I'm just going to pull up Desmos here and type in the mean of list 1. And then for list 2, might be the same here. Okay, so they're both 3.5. That helps because I can just get rid of where the means are different in C and D. And then standard deviation can be kind of tough. The two different standard deviation problems we have are whether they're the same or different and whether one is greater or less. So it's kind of easy whether they're the same or different. Your numbers are just going to have to be the same. So in this case, our numbers are just different. So we know that our standard deviations are different. But let's try to look at like a different example. A different way, if they wanted us to say which of these lists had higher or lower standard deviation, all you have to think about is if we're focused on distance from our center, right? The greater distance from your center, the higher standard deviation. So I look at my first set of differences. This goes to 4, this goes to 4. This goes to 3, this goes to 3. So technically they would have the same standard deviation at this point. If I go to my next number here, this one jumps up to a 5 and this one jumps down to a 2. They're both jumping a digit away from where our center was established. Whereas this stays as a 4 and this stays as a 3. That's all I need to see. This is going to be higher standard deviation because there's a greater distance from our center. And then this lower list is going to be a lower standard deviation because there's less change from our center. The way you're going to see standard deviation, though, is usually in the form of a graph. So imagine I had a couple numbers down here were like 1, 2, 3, and 4. Also 1, 2, 3, and 4. And we'll call this list A and list B. And we'll give it some data points here. We'll say list A looks like we have a little bit, we have a little bit more, we have a lot at 3, and a little bit at 4. Down here, it's all over the place. A lot, a little, a lot, a little. So what you want to do is you want to focus on the essence of like this pyramid graph. If I can draw this nice, neat pyramid that kind of centers around a focal point of our data, this again is going to be low standard deviation because we have a focus, we have a center, and there's less change away from our center. Over here, I would draw my center here, and I have a lot of change. I have a little bit here, a lot here, a lot here, and a lot here. So this is going to be high standard deviation. This is usually how you're going to see standard deviation portrayed. Number 12, I see a book was on sale for 40% off its original price. So for these ones, immediately just jump into, we have our original, we have our, we'll call this like our sale, and not just currency, but I want to think variables. If you always want to give your start a 1x. So if I started at 1x and it's 40% off, that means the remaining cost is going to be 0.6x. Well, what's nice is they also gave us the numerical cost of when it's 40% off, and that's going to be 18. So all I have to do is set this equal to the 18 that it is, worth now. I divide this by 0.6, and I should get 30 as my answer. So this works even up to like the hard percentage problems. Always give your starting, what you started at, 1x, do your change in a variable, and then set it equal to the change that they give you numerically. Just going to be C here. Number 14. I see of the following, which is the closest to the ratio? So remember, ratios can be written in 3 ways. I could say 2 to 5, I could say 2 to 5, or I could say 2 over 5. They want the ratio of the total number of insects in week 8 compared to the total at initial. So again, how I would write this is if I have the total in week 8, I would then divide it by the total at week 0. And I should get something close to one of my answers. So let's estimate a little bit here. In week 8, I see that might be like 19. I see that could be like 10. And then for this one, you might say 50. I think I'll say 51 just to keep this like a nice even number. So that's going to get us 80. And then for the next bar here, over in week 0, I see that's definitely 80. And then this one, maybe I would call that like 62. And then this one, again, a little bit below, maybe we call it 58 just to keep it nice and even. So that should add up to about 200. And that gives us a nice, and then at this point, instead of trying to reduce my fraction to see which one it matches, we just get decimals, right? If I divide this, I get 0.4. If I divide all of these fractions for A, I should also get 0.4, and that's going to be our answer. Not too bad ratio practice there. 16. Anytime I see years in a problem, I'm always going to make this into a chart problem as opposed to like making equations or using Desmos. So what I can do is we have 2010 to 2015. And I see that we have city X and city Y. So it looks like we're going to have maybe changes between these two, something like that. And now we can just try to fill in the blanks here. So in 2015, they were equal. So I can put a little equal sign here. The population of city X increased by 20%. So right here, we're going to have like a plus 20%. And the population of city Y decreased by 10%. So we're going to have a minus 10% here. And then they have to give us a number. City X was 120K in 2010. So I can say 120K here. And then from here, it's not bad at all. To add 20%, I like to just multiply by 1.2 instead of times 0.2 and then adding it on. It does it in one step. So if I multiply 120 by 1.2, I should get 144K here. And then again, we know that they're equal in this year. That's why I made this chart. So this is also going to be 144K. And then here's the weird part, but if you watch my percentage problem from earlier, you're going to remember. You always want to assign one X. There's X and Y here, so maybe I'll do like 1A here. You always want to assign a variable with a coefficient of 1 to our unknown start. So if I call this 1A, and I know that 1A loses 10%, well, what's minus 10% from 1? And that's going to be 0.1. So this ends up actually at 0.9A. And then what also lost 10% to get to 144K. So these are both just the result of losing 10%. This sets us up so we always know what to multiply, what to divide by. Now I just divide this by 0.9, and I should get 160K for my start here. So again, if you ever have an unknown start percentage problem, give it 1x, give it 1a, do the deduction or the increase of a percentage decimal form, and then set it equal to your numerical result. That's it. It's going to be C here. Number 18, you're really only going to have two types of probability problems. You're going to have your easy versions where it's just very standard. What is the chances of this out of a total of this? And then you're going to have your given probability problems. So let's see the context, right? So based on the table, which of the following is the probability that they answered always? So normally, if we pause there, that would be the easy version. I would just take always, which is this percent, and I would divide it by all 4 added together. And it looks like it's probably going to be like 100%, so you would actually just end up getting A here if it was the easy version. But they're saying, given the tablet user did not answer never. So givens change kind of the dynamic of the problem. If we know the user didn't answer never, we'll be very literal. I can just get rid of this from my table. So we still proceed as if it's a standard probability problem, it's just our pool has changed. So we still want the probability that it's always. So that's our numerator, 30.9. And then we still want our total, but our total now doesn't include never. So if you add those 3 up, I think it's like 67.8 or something like that. And then when you divide this, of course, our chances have now increased because we're not including never. That's all you ever do for given problems. Though there's a Blue Book one where they make it more complex. You just make a big chart, get all your data points, get rid of the numbers they do not want because of your given, solve normally. That's it. Number 23. If I ever see a chart, my first reaction is open up Desmos. And on Desmos, again, the reason I see a chart and I think Desmos is I can add a table and I can make my own chart. So they did establish that this was linear. So I'm only going to need 2 points. If it was, exponential, a parabola, I would use 3 points. So we only need 2 points here. I see A and 0, and I see 3A, and I see negative A for my Y. And you're going to see these, that's just because there's a letter. So if you ever have a letter in your chart, you're just going to have to define A for Desmos. So I just say A equals 1, And then remember to graph our line, it's going to be this right here. So this is a representation of our data points as a graph if our a is equal to 1. And it's nice, they're just asking for which one of these represents the table. So the easiest possible way to do this one is I'm just going to type in my answer choices and see what matches. This, they're saying, could represent our line. So it's either going to match or not match our line. Right off the bat, a is going to match. Worst case scenario, you have to type in a couple equations, like if D is our answer. But again, you're just looking to type these in until one of your lines matches your table. It's going to be A here. Number 29, it looks like we have a linear equation word problems. These can get pretty difficult. I think this is one of the harder versions. So right off the bat, let's just remember that when we describe our linear equations in context, they're always going to describe your y-intercept as like a start, as an initial, and your m, your slope, is always going to be some sort of a rate. On top of that, to get a little bit more advanced, if we did make a little t-chart over here with our x and our y, always remember that your x is your input. You would always be inputting a 1, a 2, and a 3 into your x. And if I made a little simple equation, y is equal to 2x, it's not our slope while it's next to our x is actually not affecting our x. Our x is independent. When I plug a 1 into x, my y turns into 2. When I plug a 2 into x, my y turns into a 4. The slope is actually affecting our y. So now getting into this problem, when I notice that, my 32, if they did mention it, it would always be described as like it's a start. We begin at 32, whatever the units are. When I look at my slope, this 1.88, per increase in my L, per increase in my x, my y is going to increase by that much. So let's look into it. I already see at the end of this, they say, what is the meaning of the 1.88? So it's going to be our slope. So I already know 32.01, 32.01 is going to have nothing to do with it. So let's see which one of these describes it better. C is saying the increase in a man's femur length, L, in inches for each 1 inch increase of the height. So wait, hold on. This 1 inch increase of the height, my input is supposed to be my x or my L. This is saying when I input 1s into my height, my y, we don't do that, right? Let's just make sure that D makes sense though. The approximate increase in a man's height, how does my y change for each 1 inch increase to my L or my x? D describes this relationship perfectly. If you can get this one, it's going to be really hard for them to confuse you on these linear equation context problems. Number 30, two-dimensional geometry problem. Almost always, your goal is to see if you can form a right triangle in these. It doesn't matter if it's a circle, a quadrilateral, etc. Because if you can make right triangles, you can solve the rest of your shape. So already your inclination should be, again, if I can make a right triangle here, I could just draw this straight down, right? And it makes it into this nice rectangle. I don't know if it's a square, but we do know this is a right triangle, and we have a lot of roles associated with it. Let's see what else they say. CD, this over here, is going to be 1/2 of AB. So anytime you see relationships like that, always try to like plug numbers in. So if CD is 1/2 of AB, really the easiest numbers I could come up with are give 1 to your smaller and give 2 to your bigger. Technically, I don't know what ratio they are. I don't know if it's 1 and 2, 2 and 4, 5 and 10. So I can associate them both with X as like my multiplier. And then we should also see that because BC is parallel to AD, this line, this CD line, it's almost like they're just taking it and shifting it over. So this should be the same length as that. And then finally, the reason why we aim for right triangles, you see a 1x, you see a 2x, you should pull up your equation sheet and look at your special triangles. On there, you're going to see your special triangle, your 30, 60, 90, and it's going to be 1x for your shorter side, 2x for your hypotenuse, and x squared of 3 for your like medium length side. And your angles are going to be 30 for your opposite of your smaller side, 90 for opposite of your bigger side, and again 60 for opposite of your medium side. So this is what I see on my equation sheet. I can just match it up to my triangle here, and I can say, I know everything now. If this was like a solve for your sides, I would probably say, okay, I know this is x squared of 3. Fortunately, all they're asking for is the angle of B. So we know this part of B is going to be 90. And then now I know that this part of B, it's going to be the one that's opposite of my x squared of 3. It's just going to be 60 there. So no Pythagorean's theorem, no having to do sine, cosine, tangent. I know that the total angle of B is just going to be 150 degrees. That's it. Number 35. I see the key phrase, infinitely many solutions. You're only going to see infinitely many solutions with two linear equations. And again, if we're building off of the no solution problem we did earlier, all I'm going to have to do is think these two lines are overlapping. Graphically, that's going to mean they have the same slope and the same y-intercept. So again, just because you get some funky numbers with this sometimes, on Desmos it can be a little bit hard to read the weirder fractions. I just always do these ones by hand. First, I have to get them both in slope-intercept form. So I just distribute this, and I get ax plus ab. And because it's infinitely many, I know that my slope and my y-intercept are equal. So I know that my 4 is my slope of my other line. My a is my slope of this line. So I already know a is equal to 4. And then for my second equation, we know that our y-intercept is 10. For them to be identical, my AB has to be equal to 10. And if I know that my A is 4, it's just 4B is equal to 10. Divide this by 4. And for B, you should get 2.5. So really, not too bad there. Always just put them both in slope-intercept form if you see no solution linear equations or if you see infinitely many. That's all. Number 36, I see that we have an equation y equals c. What's cool is, so they tell us c is some constant. If you ever forget what like your x equal or your y equal lines look like, just jump in Desmos, do like y equals 5, right? Your y equals are going to be horizontal lines. Your x equals are going to be vertical lines. So we know that this horizontal line intersects a parabola exactly once. We already have this problem categorized, right? If you ever have a parabola and you have a horizontal line, there's only a single point on a parabola where it can intersect once. And that's going to be, let me shift this down a little bit. That's always going to be at your vertex, right? So if I just throw this guy in Desmos, let's shift this over to the side here. And we do y equals negative x to the second plus 5x. I don't even have to draw my horizontal line because I know a horizontal line can only intersect a parabola at one point, and that's always going to be at our vertex. I just want to double check which point do they want, and it looks like if I shift this over, they want the y value, right? The c value is a y value, so for my parabola, that's just going to be 6.25, and that's all you have to do for that one. Number 37, I see that this falcon can reach speeds of 200 miles per hour while diving. What is the falcon's maximum speed while diving to catch prey in feet per second? There it is. This is going to be our standard unit conversion problem. And again, I have a systematic way that I love using. We're going to start at 200 miles per 1 hour. And we're just going to make a chart and convert unit by unit. So let's start with miles. I know that right here in 1 mile, there's going to be 5280 feet. And then just to stay organized, I know that my miles are going to cross off. And now I have feet per hour. And now for hour, again, we're going to have to convert this to seconds in 1 hour. I know first that there's 60 minutes. And then I can do in 1 minute, there are 60 seconds. And let's just make sure everything cancels out. I know that hour cancels out with hour, minute crosses out with minute, and then I have feet per second. All you have to do at this point, we can just pull our Desmos up, shift it over to the side, and I'm just going to use it to calculate. I'm going to do my numbers here across the top and across the bottom. 200 times 5280 times, there's only ones left above there. And if you ever have plural units here, just in case I don't accidentally divide by the 5280 alone, I do a parenthesis, divide, and then on the bottom I only have 60 times 60. And it looks like we're going to get about 293. They do tell us to round to the nearest whole number, so I would get 293 feet per second. Not too bad. Number 38. This is an extension from the last problem where we got for our final solution, this falcon can travel 293 feet per second. Earlier on in the problem, they also told us that it could travel 200 miles per 1 hour. So when they say that, it's diving at its maximum speed for half a mile, you might think, okay, well, we already have a miles per hour equation. We could try to figure this out in how many seconds it would take, right? But it probably would be easier. What if we used our already per second equation and we were able to turn their half a mile into feet? So also earlier on, just in case you didn't know, they told us that 1 mile would be equal to 5280 feet. So we want to try to think, instead of going with our original equation, which is just going to take more time, let's go with a half a mile would be equal to 2640 feet, because all I did was divide that by 2. So if we use our rate now above right here, 1 second takes 293 feet. And then again, I throw my 2640 feet for the distance that we want to travel. My feet are going to cross off. And I do 2640. Let's go ahead and open up Desmos real quick. I do 2640 divided by 293. And we get something close to 9. They do tell us to round to the nearest second, so it looks like I'm just going to get 9 seconds here. So you could have used either rate. Doing the 200 miles per hour would just take longer. There's more conversions you have to do. Try turning your half mile into feet. Use the solution we got from 37. That's it, 9 seconds here.
Anywhere you go, you belong. Anywhere you say,